Today we're going to be talking about circuital laws. This should largely be a review of stuff that you guys learned in your Engineering 120 series, but as per usual, we're going to go into a little bit more depth so that we have a good understanding of what's going on, right? So let's start by talking about Ohm's law, resistance, and conductance. So way back in the 1830s, I believe German physicist by the name of George Simon Ohm started doing some experiments with this newfangled thing called electricity. And the experiments that he did were something akin to this. Okay. So he took a source and he connected said source to a material under test. So material under test, okay? And what he did is he measured the voltage drop across the terminals of the material under test, which I'm just gonna label as a generic voltage V. And he measured the amount of current flowing through the material under test, which I'm just going to label I. Does this experimental setup look familiar to you guys? It should, because I made you do it in the last class meeting. Okay. What he found is that there was a constant of proportionality between the voltage across the terminals of the material under test and the current flowing through the material under test. So when you guys did your experiment, you probably did something like this, where you plotted voltage as the independent variable and current as the dependent variable. And you should have gotten a graph that looks something like this. Okay? So we can see that there's just a simple linear relationship between voltage and current. Ohm's law effectively says that the ratio of the voltage to the current is known as resistance R. Now, this resistance R is actually the inverse of the slope that you guys found, because if you plot I on the vertical axis and V on the horizontal axis, you actually get a different constant of proportionality. So the ratio of I over V gives us conductance G, okay? So let me just label things here really quickly. So R is for resistance, G is for conductance, okay? So we can think of resistance as a measure of how difficult it is to pass charge through a medium. I hesitate to use the word material here because realistically, there is a material property that is very related to resistance called resistivity that we're going to bring up in a little bit. And similarly, our conductance is simply a measure of how easily or how easy it is to pass charge through a medium. Okay. So let's look at our units here. Okay. Actually, before we do that, I'm going to introduce the schematic symbol for a resistor, which you all should know, hopefully, at this point. So over here on the left-hand side, I'm going to have the schematic diagram symbol for a resistor. And so we would have this in, label it as R, and we can see from the units that resistance is just the ratio of voltage to current. So we're going to have what we call an ohm. So 1 ohm, symbol capital omega, is simply 1 volt per ampere. And then over here on the right-hand side, I'm going to draw the schematic symbol for a conductance. You may be thinking to yourself, gosh, those look very similar, and they are. They are literally the exact same symbol. So the only way to really tell the difference between a resistance or a conductance on a circuit diagram is to look at the units, okay? So let's figure those out really quickly. So conductance is defined as the ratio of current to voltage. So it's going to be measured in amps per volt as our fundamental units. And we call that amps per volt a Siemen, S-I-E-M-E-N. The symbol is capital S. This is the same Siemen that originated the Siemens Electronics Company that you may be familiar with. So this is just simply 1 amp per volt. So it should be fairly obvious that there is a relationship between resistance and conductance, where they are simply the inverses of each other, right? So we could say that resistance is simply 1 over conductance, and similarly, conductance is just 1 over the resistance. Now, let's talk a little bit about where conductance is used. So, other than today, I'm probably not going to even mention the topic of conductance again for this entire class. So anytime that you guys are dealing with a circuit that contains conductances, your best course of action is simply to take the reciprocal of it and then treat it like a resistor, because we don't need to bog ourselves down with special rules on how to combine them and all of those kind of things. Now, I feel pretty darn safe in telling you guys to do that because I've taught this class like 30 times at this point or whatever, and I know what's coming. But even for you electrical engineering folk, we're not really going to use conductances for anything until we get into our electronics courses. And then we're just going to use conductances as opposed to resistances, because we're just going to have tons of things connected in parallel, and it just makes the math slightly easier. In practice, conductances are used to describe properties of transmission line networks and things like that. Which, unless you're going into your senior electrical engineering classes in particular, you're not going to have to deal with that at all. So largely, you can just forget about conductances as being a thing if you choose to take the reciprocal of them and then just call it a resistance. So that's what we're going to do for the most part in this class. Okay, so a couple of things. First, let's play around with Ohm's law a little bit, particularly with the context of a resistance. So we are used to the relationship where I'm going to draw a resistor here. I'm going to draw a voltage, positive polarity on the left, negative polarity on the right, and I'm going to draw a current flowing in to the positive polarity terminal. Okay? So in this particular configuration, Ohm's law looks like V is equal to I times R, which is what you guys learned in your Engineering 120 series courses, right? But if I take that same resistor and I define the voltage in the opposite polarity, the current in the same direction, in this case, we're going to say that V is equal to negative I times R. This is something that you guys definitely did not do in your Engineering 120 classes because you really only ever had one voltage source, so the polarity of the resistors was always effectively fixed. But because we're going to be dealing with complex circuits containing multiple sources, we now need to introduce this additional small level of complexity to Ohm's law. So effectively, whenever our current is flowing into the positive polarity terminal of a resistor, we have a positive sign. Whenever our current is flowing into the negative polarity terminal of our resistor, Ohm's law gets a negative sign. So let's talk exactly about why we need that. Okay. So what does a resistor do? Resists current, okay. So how does a resistor resist current? What, I think I heard it, creates heat, okay? So all a resistor can ever do in any circuit, doesn't matter what its application is, so they're usually used to limit the amount of current or something like that, but all a resistor can ever physically do is convert electrical energy into heat energy. That is it. A resistor is fundamentally incapable of storing any energy at all, which means we can never have a supplied power with a resistor because it can never store energy to supply it to anything else. So we need this negative sign in Ohm's law when the current is flowing into the negative polarity terminal to force the resistor to always be absorbing power or always be converting electrical energy into heat energy. So that's why we need that negative sign there. Let's look at an alternative definition for resistance. This is a relationship that I believe that you guys used at least at some point in the Engineering 121 class, but we're going to take a look at it here, and it's going to help us explain a couple of assumptions that we've made previously. Okay. So resistance R can be calculated for a given medium as rho subscript E. So that is the electrical resistivity. So let me put a note there. Resistivity measured in ohm meters, typically, times the length of our object divided by the cross-sectional area of our object, where length is typically measured in meters and cross-sectional area is typically measured in meters squared. So dimensionally, we can see very easily that if we have ohm meters times meters over meters squared, the output of this calculation is going to give us something in ohms, okay? So let me make sure we all have a good understanding of what those dimensions mean by looking at a wire, okay? So let's say that I have a wire, and these squiggles here are just meaning that I don't want to draw a whole really long wire, so I'm just subdividing it into two parts. So if the current is flowing down the longitudinal axis of the wire, then this dimension is the length of the wire, and the cross-sectional area of the wire would simply be the area formed by the wire's circular surface. So technically speaking, if we were able to flow current through the wire, like, for lack of a better term, a jackass, so in the top and out the bottom instead of down the length of the wire, it would see a significantly different resistance. Wires don't really work that way, but if we could do that, we'd need to pay attention to that. This definition for resistance comes into play a lot when you're designing microstrip transmission lines and things like that for making integrated circuits, to where you're using long runs of wire that have a specific rectangular cross-sectional area based on the thickness of the copper trace and all of that kind of stuff. But anyway, I want us to look at this thing, this relationship, and I want us to calculate the resistance of a section of wire like what we've used in our previous classes, okay? So let's say that we have a section of 22 AWG copper wire, okay? So what I would like one of you guys to do is to give this a quick Google and tell me, because I don't remember it off the top of my head, what the electrical resistivity of copper is. I feel like it's somewhere in the ballpark of like 1 point something times 10 to the 8 ohm meters, but I may be misremembering because I'm an old man. Ohms. 1.68 times 10 to the negative 8. Is that ohm meters or ohm centimeters? Ohm meters, okay. Now, could you look up the diameter of 22 AWG copper wire? Feel like that's a little bit less than a millimeter, but I don't remember off the top of my head. And if you give it to me in inches, that'll be okay, because we're smart enough to do simple conversion between units.
I think it's 0.0253
0.0253
inches.
inches. Thank you, Carolyn. And ballpark how long the wires, like the longest piece of wire that you guys used to build a circuit before was? Probably just a couple of inches or something like that, right? So let's say maybe 5 or 6 inches. I feel like the twisted pair that you used to connect the 5-volt pin and the ground pin to your board was told, you were told to make it 5 inches long in the spreadsheet. So let's say that our length is 5 inches. So let's put these things together real quick and calculate the resistance of a wire with these dimensions, okay? So we'd have 1.68 times 10 to the minus 8 ohm meters times our length of 5 inches times a conversion factor of, let's see, so it's 2.54 centimeters per inch. So that would be 0.0254 meters per inch, if I did my mental math there correctly. And then we have the cross-sectional area, which is related to the diameter by pi over 4 times the diameter squared. So 0.0253 inches. I feel like I have a mistake here just because 0.0254 meters is almost the exact same thing as 0.0253. Oh, no, that's just a coincidence. I'm just dumb. It's too early in the morning and I haven't had enough coffee. My bad. Okay. So squared and then times 0.0254 meters per inch. And then we need to square that conversion factor. So let's throw this in a calculator really quickly, just to see what shakes out. So 1.68 times 10 to the minus 8, 0.0254 divided by pi over 4 times 0.0253 squared times 0.0254 squared. I got, and you can tell me if I got the wrong answer, 0.006578 ohms, or 6.578 milliohms. Anybody else get something relatively close to that? Okay. So what was the smallest resistor that you guys used to build a circuit in your engineering 120 classes? I think it was the one that you used to make sure your LEDs shone very brightly. So what kind of resistor was that? Ballpark it. I don't expect you to remember exactly. 220, exactly right. So the smallest resistor that you guys used in your previous classes was 220 ohms. How does 220 ohms compare to 6.578 milliohms? Several thousand times larger, right? So the reason why you were able to treat all of your wires as if they didn't have any resistance is because of this equation. As long as we don't make the wire incredibly long or have an incredibly small cross-sectional area, the wires don't really contribute a whole heck of a lot of resistance as compared to the size of the resistors that we use to create our circuits. Now, if you're working at an industrial plant or something like that, and you're having to set up a really, really long cable run to go from a control room out to some sensor, the length of that wire might be long enough such that the resistance is actually appreciable. And so those are things that you're going to have to take into account when you're dealing with practical electric circuits. Everything that we're doing with this class is kind of a lab scale thing, so we are going to treat all wires as if they have zero resistance or they are a short circuit. But in real life, the resistance of a wire matters. Okay, so I just want to make you guys aware of that. Particularly those of you that are going to go out and work on internships at manufacturing plants and all of that kind of stuff where you're integrating sensors, setting up electric motors, HVAC systems, all that kind of stuff. The resistance of your wires really, really matters there. Okay, so I just mentioned the term short circuit, okay? So we are going to kind of define two very special resistances here. So when we have a short circuit, that is just going to look like a section of wire or a straight line. In this class, we will treat all short circuits as having a resistance of 0 ohms. And since our resistance is 0 ohms, what does that tell us about the voltage drop across a short circuit? So if V is equal to I times R, and R is 0, V has to be 0, right? So anytime we're dealing with a short circuit, it will always have a 0 volt drop across it. Okay. On the flip side of things, We will also deal with what are called open circuits. And we'll represent an open circuit as effectively just a break in the wire. Well, for an open circuit, we are going to consider it to have an infinite resistance. And so if it has an infinitely large resistance, what does Ohm's law tell us the current has to be? So current I is going to be equal to V over R. If R is infinity, we have whatever the voltage drop occurs across the terminals of our short circuit divided by infinity. So it's going to be 0. So the current that flows through a short circuit is always going to be 0 amps. So we know fundamentally that a wire has some amount of resistance. So realistically, we could have a very small voltage drop across what we would consider a short circuit in practice, right? Is there an analogous thing for open circuits? Well, absolutely. Okay. So we can push current through an open circuit if the voltage is high enough to literally ionize the medium between the terminals of the open circuit. So if this outlet right here is an open circuit because nothing is plugged into it. But if I take a piece of wire and I get it really, really close to touching the metal contacts, we'll probably see some sparks as current flows because that voltage coming out of the outlet, which is roughly 170 volts as an AC waveform, if I get within probably half a millimeter or so, that's enough to ionize that air and cause current to jump across that small gap and complete the circuit. Okay, don't do it. It's kind of dangerous, but you've probably all seen it before when you go to plug something in or when you go to unplug something, particularly if it's something that automatically turns on whenever you plug it in. So anyway, so there is a practical case where current will flow through an open circuit, but it usually involves sparks and potentially a fire. So, be careful. All right, so let me think here. We've talked about what Ohm's law is fundamentally. We've gone over the units. I think the only thing that I really have left to do is to just bring up those simple power relationships that you guys learned in Engineering 120, just to refresh your memory, right? So I'll continue to do resistor stuff on the left-hand side and conductance stuff on the right-hand side. We know in general that power is equal to current times voltage. And we know that voltage is equal to current times resistance. So from this, we can get the relationship power is equal to voltage squared divided by resistance or current squared times resistance. So whenever we have a resistor, we only need to know either the voltage or the current in order to calculate the power. We don't have to know both quantities. Okay. For conductances, our power is still going to be I times V, but our Ohm's law is going to be a little bit different. So for conductances, Ohm's law looks like I is equal to V times G. And from this, we can say that power is voltage squared times conductance or current squared over conductance. All right, does anybody have any questions about Ohm's law as it pertains to this particular course? The biggest thing that's going to bite you guys in the butt is remembering to include that negative sign where it's appropriate. Okay, so just be on the lookout for that. So now that we've got Ohm's law taken care of, we're going to move on to Kirchhoff's circuit of laws. And I'm going to explain one of them in detail, then the other in detail, and then we might kind of jump back and forth between them to help us kind of sort out some commonalities in the circuits that we're going to see. Okay. So let's start with Kirchhoff's voltage law. And I will probably just call it KVL from here on out. So Kirchhoff's voltage law states that the sum of the voltage drops around any closed path, and I'm going to underline that because we need to talk a little bit about what that means, must equal to 0. And in a mathematical form, we would simply say that the sum of all voltages in a circuit is equal to 0, where I is from 1 to n. So if there are 15 components, they all have to add up together, or 15 components in a closed path, they all have to add together to make 0, effectively. Okay. So let's talk about this idea of a closed path really quickly. Okay. So what I mean by a closed path is actually pretty different than the loops and stuff like that we talked about on our first day of class. So a closed path in terms of Kirchhoff's voltage law just means I start and end at the same node. Okay. So I know that you're probably thinking, well, how is that different? So let me give you a specific example so that we can see how things will be a little bit different. Okay. So let's say that I have this circuit. I have a 5-volt source, a 3-volt source, here I'm just going to put a resistance. Let's say, just for the sake of argument, that it is 12 ohms. And over here, I'm going to put a 2-volt source, like so. So the first thing that we're going to do here is we're going to use Kirchhoff's voltage law to determine the voltage drop across that 12 ohm resistor. And I am going to choose, just for illustrative purposes, that this voltage drop will have its positive polarity terminal on the right. Okay? There's nothing about the resistor itself that's telling me put the positive polarity terminal on the left or put the positive polarity terminal on the right. It is just an arbitrary decision that I have made, and this is an arbitrary decision that you guys will make over and over again in this class. Okay. So whenever we aren't told, we just choose. And as long as we're applying Kirchhoff's voltage law and Ohm's law correctly, as are necessary, then our decision of whether the positive polarity terminal is on left, right, top, or bottom literally does not matter. So how I like to apply Kirchhoff's voltage law is I typically start at the bottom left-hand corner of my circuit, and then I simply add up all of the voltage drops around my closed path. Okay. So if I were to apply KVL around this circuit, and I'm going to call this KVL around the outside, and you'll see why in a moment, because we're going to do something with the inside. this would look to me like negative 5 volts. And I put a negative sign there because we see the negative polarity terminal of that 5 volt source first. Then I'm going to have plus 3 volts because I see the positive polarity terminal first. Then I'm going to have minus V12, the voltage that we're looking for, and then plus 2 volts is equal to 0, because now we're back down to that bottommost node. Okay. So before we move on from this and do the very small amount of algebra to sort things out, does anybody have any questions about where any of those signs came from? All of that makes sense. Good deal. Yes?
First, 5 volt understanding of music.
So we're starting from here, and we're going around in this direction. So because we see the negative polarity terminal first, we get a negative sign. So anytime we see the negative polarity terminal first, we put a minus sign. Anytime we see the positive polarity terminal first, we see the positive sign. Okay. So we could rearrange this thing very quickly. So I'm just going to move that V12 to the opposite side of the equal sign, and I'm going to leave all of those constant voltages there. So we'd have negative 5 volts, plus 3 volts, plus 2 volts. So I accidentally chose numbers that wound up giving me 0. That's okay. Literally doesn't matter. If we had chosen the opposite polarity for our voltage, so positive polarity on the left-hand side of V12, negative polarity on the right-hand side of V12, would that change our result? No. Would our result change if we applied Kirchhoff's voltage law and went around this loop in a counterclockwise fashion as opposed to a clockwise fashion? Also, no. We are going to get the exact same result every time. Now, if the answer were non-zero, so let's fix some things here and say, this is 1 volt, so that my answer is no longer 0. We would get, let's see, negative 5 plus 4 is minus 1 volt. So if I flipped the polarity of that voltage V12, what answer would we get? Positive 1 volt, because flipping the polarity of a voltage is the same thing as multiplying that voltage by a factor of -1, as we discussed in our previous class. Okay. All right, so now let's mess around with our idea of a closed path. What if I want this voltage Vx? First, is this fair? Is there anything intuitively telling us that we can't determine this voltage? So a lot of people seem to think that whenever we're applying Kirchhoff's voltage law, we need to be as part of a closed path where like current could flow. But really, I'm just looking for the voltage drop across an open circuited set of terminals here, okay? So if I drew this open circuit, we would just be finding the voltage drop between these 2 points in this particular circuit, which is all a voltage is. Finding our voltage here using Kirchhoff's voltage law is effectively the exact same thing as just using a multimeter to find the voltage between 2 points in a circuit. Okay? We're just using other known quantities instead of a tool to do it for us. Okay? So I could, if I were so inclined, write a KVL equation around this path or this path, and these paths could go in the opposite direction if we wanted to, and that would be a perfectly appropriate way for me to find that voltage Vx, okay? So let's write KVL around the gray loop. So we would have negative 5 volts plus 3 volts plus Vx is equal to 0. And then we could solve that and say that Vx is going to be 5 volts minus 3 volts is 2 volts. If we wrote the KVL equation around that light purple loop, we would have negative Vx minus V12 plus 1 volt is equal to 0. We're going to substitute in negative 1 volts for V12. So that's going to give us negative Vx minus negative 1 volt plus 1 volt is equal to 0. And solving this guy, we would get Vx is equal to 2 volts. So it literally doesn't matter which of those two paths we use, we're going to get the same result for Vx. So just to recap things here, when I'm applying Kirchhoff's voltage law, all I'm doing is adding together voltage drops. Current does not make any difference whatsoever. As long as I can define a voltage drop between 2 points in a circuit, I can apply a KVL loop and figure out what that voltage is. Okay. Now, we can use Kirchhoff's voltage law in conjunction with Ohm's law to find things like currents and all that kind of jazz. So let's work an example problem. And this is going to be a pretty fair increase in difficulty. So let's say that I have the following circuit. I have here an 8-volt source. Here will be a 5-ohm resistor. I'm going to define this voltage drop as Vx. Down here, I'm going to put 10-ohm resistor. Let's make this a 12-ohm resistor. And lastly, let's put a dependent source here. That is 2Vx. And ultimately, I want to figure out the current I that is flowing clockwise around this circuit. So the only voltages that are defined in this particular circuit are our independent source voltage of 8 volts, our dependent source voltage of 2Vx, and then that voltage drop across the open circuit in the middle, that's Vx. So we aren't told the polarity or the value for the voltage drop across any of our resistors, okay? So that means that we have to make a decision. So I normally, in the course of working problems personally, wouldn't do this, but I'm going to choose different polarities for my voltages, okay? So what I mean by that specifically is I might choose a positive polarity for my 5-ohm resistor. The positive polarity is on the left, and then just to be a weirdo, I'll put the negative polarity on the left for my 12-ohm resistor. And I'll let you guys choose what the polarity for my 10-ohm resistor should be. Positive on the left or positive on the right. Doesn't matter. Okay. Positive on the right. Okay. So this is our circuit. So let's see what happens if we write a Kirchhoff's voltage law equation around the outside or the perimeter of the circuit. So somebody tell me what's that's going to look, or what that is going to look like. And let's just start by putting everything in terms of the voltages that we've labeled. We'll integrate Ohm's law in a couple of minutes. Okay. So starting at the bottom left-hand corner and going up, what do we see first? -8 volts. Okay. What do we see next? Positive V5. What's next? After that? And then after that? Positive V10. And we set this equal to 0, right? So we started and ended at the same node. So our path is closed. Okay. So as it stands at this exact moment, we have one equation with 1, 2, 3, 4 unknowns. So we've got some work to do. Okay. So let's start by applying Ohm's law to get rid of some of those resistor voltage drops and put them in terms of that current I that is common to every element in this circuit, because there's nowhere else for that current I to go. So that same current I flows through everything. Okay. So using Ohm's law, how would we put that voltage V5 in terms of our current I? So let's start with, what's Ohm's law? Somebody throw it out at me. V is equal to I times R, okay? So I, in this case, is literally just I, because I labeled it that way. What's R? 5 ohms. So we'll just have 5 ohms times I. Now we need to check. Is our current I flowing into the positive polarity terminal of the voltage V5 or into the negative? It's into the positive polarity terminal, so Ohm's law should get a positive sign. So we're going to leave that alone. Okay. What about V12? How am I going to put that in terms of my common current I? So I hear some people saying -12 ohms times I, and I hear some people saying +12 ohms times I. Tell me why it should be negative. Because the current's flowing into the negative polarity terminal, right? So -12 ohms times I. And then lastly, we have V10. So what should that be according to Ohm's law? 10 ohms times I, and it's positive because the current is flowing into the positive polarity terminal. And so now we can substitute all those things in, right? So let's do that here below. Okay. So we would have V5, which is just 5 ohms times I, minus V12. So we're going to have minus -12 ohms times I, plus twice Vx, plus V10, which is 10 ohms times I, is equal to 8 volts. I just moved that constant term to the right-hand side of the equal sign. And we can see now that we could lump together, so we would have 5 ohms minus -12, so that's 5 plus 12 is 17. plus an additional 10 ohms times I. So 27 I plus twice Vx is equal to 8 volts. Are we okay with the substitutions and the algebra that I've done there? Nothing hopefully too wild or crazy. All right. So Ohm's law got us from one equation with 4 unknowns to effectively one equation with 2 unknowns. So really, now we're just trying to figure out another equation that's going to relate I and Vx so that we can solve that simple 2 equation, 2 unknown system, right? So we could either write a KVL expression for the left-hand portion of the circuit, or we could write a KVL equation for the right-hand portion of the circuit. Which one would you guys prefer? So we'll do it for the left, but I think the right-hand portion would actually be better. Okay, so let's see. Okay, so KVL for the left. We would have negative 8 volts, and then we'd have plus V5, but I can go ahead and substitute in for V5. So let's call that plus 5 ohms times I1 plus Vx plus 10 ohms times I1 is equal to 0. Grouping things together, that's going to look like 15 ohms I1 plus Vx is equal to 8 volts. The reason why I think things will be slightly better or whatever if we do the right-hand side is, let's do it just for the sake of argument. This is actually providing us effectively the same information, or at least enough information to do things. But we would have negative Vx plus, excuse me. No, it'll still be plus 12 ohms I. So just to be clear there, I'm doing minus V12 where minus negative 12 ohms times I is plus 12 ohms times I. Plus 2Vx is equal to 0. And this tells us that Vx is just negative 12 ohms times I, so we could directly substitute in. Okay. But it doesn't really matter. We have now, because we did the work, 3 equations and only 2 unknowns. So realistically, we only need 2 of those things to solve our whole system. Okay. So what I'm going to do is I'm going to substitute this guy into here because my ultimate goal in this problem was just to determine the current I. So we have 27 ohms times I plus 2 Vx, where Vx is negative 12 ohms times I is equal to 8 volts. So that looks like 27 ohms times I minus 24 ohms times I is equal to 8 volts, or I is equal to 8/3 of an amp. If I did my algebra correctly, which is always suspect, just to be real clear. How did you guys feel about this? I think, hopefully, it might be a bit tedious, but it's not too bad challenging figuring out what's going on, right? This is largely stuff that you guys have done before, But I'm just trying to step things up to the next level where we're thinking about directions and polarity and all of that kind of stuff because they're rather important. All right, so how do you guys feel about Kirchhoff's voltage law? Okay. All right, so let's use Kirchhoff's voltage law to figure out something that you guys already know. Okay. So let's say that I have this circuit where I just have, I'm just going to call this a source voltage. This is going to be some resistor R1. Here's some resistor R2. And here's some resistor R3. So before we look at this, I want us to identify our nodes. Okay. So we're going to have a node here on the top left, a node here on the top right, and a node here on the bottom. So what can we say about how the source voltage Vs is connected to the resistor R1? Are they in parallel, series, or none of the above? They're in parallel. Both elements share the red node on top and the green node on bottom. So our voltage source Vs and the resistor R1 is in parallel. Okay. So if I wanted to find the voltage drop across resistor R1, which I'm going to call this voltage VR1, if I applied Kirchhoff's voltage law around this loop, what I would find is that negative Vs plus VR1 is equal to 0, or VR1 is simply equal to our source voltage. So effectively, whenever we have two elements in parallel, Kirchhoff's voltage law tells us that they have to have the same voltage drop across them. Okay. So anytime we have multiple elements connected in parallel, the same voltage drop occurs across all of the elements in parallel. We could also say, for what it's worth, that that voltage VR1 has to be the voltage drop across resistor R2 plus resistor R3, because that resistance R1 is in parallel with that series combination. We'll get more into that in the next class meeting when we talk about resistor combination. But anyway, so this is something that you guys were told in your previous classes, and now we know exactly why it works. It's Kirchhoff's voltage law. Okay, so now let's talk about Kirchhoff's current law. So before I tell you what Kirchhoff's current law is, I want you to understand, we're going to look at something here, and I'm going to come up with 3 different versions of Kirchhoff's current law. They are all effectively the same thing. Okay? We're going to start with the one that you guys are most familiar with, and we're going to end with the one that I use the overwhelming majority of the time. Okay? So let's look at a portion of a system. Okay? So let's say that I have several wires that are part of a larger circuit, and they terminate at some common node here in the middle. Okay. And I'm going to say that this wire up here is carrying a current I1, which is defined as flowing into the node. This current I2 will be defined as flowing into the node. This current I3 will be defined as flowing out. I4 will be defined as flowing in. And lastly, I5 over here will be defined as flowing out. So when you guys learned Kirchhoff's current law in your prior classes, how did you describe it? Or how was it described to you, I guess would be a better way to put it. Anybody remember? No, okay. Does the sum of the currents flowing in have to equal the sum of the currents flowing out? Sound familiar? Okay, so that's how it's usually taught in lower level courses. So I'm going to call this KCL number 1. The sum of the currents entering a node must equal the sum of the currents exiting a node. Okay. So if we applied this version of KCL to the system that I've drawn, where I'm going to put the currents that are flowing in on the left-hand side of the equal sign. So let me just put an equal sign here in the middle. And the currents that are flowing out on the right-hand side of the equal sign, we would have I1 is flowing in, plus I2 is flowing in, plus I4 is flowing in, will equal to I3, which is flowing out, plus I5, which is flowing out. Nothing particularly wild or crazy there, right? So let's talk about our second formulation of Kirchhoff's current law. So our second way to represent things would be to say that the sum of the currents entering a node must equal 0. Okay. So I want to be clear about what I don't mean here. Okay. So I don't mean I1 plus I2 plus I4 is equal to 0. Instead, we'll go through current by current. So I1 is entering, so it would get a positive sign. I2 is entering, so it will get a positive sign. I3 is exiting, which means negative I3 is entering, because remember that we can change the direction of a current by multiplying it by a factor of -1. So we'll have minus I3 plus I4, and then minus I5 is equal to 0. So our mathematical representation here is exactly the same thing as what we have above, except we just moved everything over to the left-hand side of the equal sign. So even though those look like different representations of Kirchhoff's current law, they literally give you the exact same result because they are fundamentally the exact same thing. Our third representation of Kirchhoff's current law will be just the sum of the currents exiting a node must equal to 0, where everything that's exiting gets a positive sign and everything that's entering gets a negative sign, right? So we would have negative I1 minus I2 plus I3 minus I4 plus I5 is equal to 0, which is just the equation above it multiplied by a factor of -1, because we're choosing the opposite direction as our reference for considering a current to be positive. So as we get acclimated with applying Kirchhoff's current law, like realistically, we can use whichever version of it makes the most sense to us. But as we're working problems, I'm going to ask you guys effectively, which version do you want to use? And then we'll work the problem that way. When we get to a topic called nodal analysis, which will happen, I think, at the end of next week, we will use Kirchhoff's current law formulation number 3 exclusively. And the reason for that is it will give us the least amount of negative numbers. Okay. So I am really bad at remembering to carry negative signs around. So I prefer to use that one for that particular analysis technique, just to make sure that I don't have 70 negative signs all over the damn place where I'm going to wind up messing up 2 or 3 of them. All right, so let's apply Kirchhoff's current law and figure some things out. Okay. So let's say, for example, that I have the following circuit. So let's say that I have a 3 amp source like so. A 6 ohm resistor. And then a 1 amp source like so. And we're going to find our resistor current using Kirchhoff's current law. Does anybody have a preference of whether that resistor current should be direction up or direction down? Up or down? Somebody pick. Up. Okay. So here is my current that I'm going to call I6, and it is direction up. So now somebody else tell me whether we want to apply KCL number 1, number 2, or number 3. Number 2. And do we want to apply it at the top node or the bottom node? Because we've got 2 different nodes, so we have 2 different options here. All right, so we're going to do KCL number 2 at the top node. Okay. So KCL number 2, we are going to be treating all of the currents that are entering the top node as positive currents, and all of the currents that are exiting the top node as negative currents. So that means our 3 amp source, is it entering the top node or exiting the top node? It's entering, so it gets a positive sign. Is our current I6 entering the top node or exiting the top node? Entering, so it gets a positive sign. Is our 1 amp current entering the top node or exiting the top node? Exiting, so it's going to get a minus sign. And then rearranging, we would have I6 is equal to 3 amps, sorry, negative 3 amps plus 1 amp, or negative 2 amps. So there's KCL number 2 applied at the top node, right? I would encourage all of you to be that formal and remind yourself which version of KCL you're using and at which node until you get comfortable with being able to go back and forth between the different variations, okay? So let's look at another problem where we are going to add Ohm's law into the mix. Okay? So let's say that we have this current, 4 amps. And then we have a 10 ohm resistor like so. And an 8 ohm resistor like so. And we are just trying to find, let me move this over. This voltage, which I'm going to call Vx. So we're going to use a combination of Kirchhoff's current law as well as Ohm's law to figure things out here. Okay? So I'm going to choose and say that the current flowing through the 10 ohm resistor, I10, will be direction down. And the current flowing through the 8 ohm resistor, which I'm going to call I8, will be flowing up so that we get more practice on applying Ohm's law correctly. Okay. And let's use KCL number 1 at the bottom node. So KCL number 1 says the currents flowing into the bottom node have to equal the currents flowing out of the bottom node. Okay. So what's our only current flowing into the bottom node? I10. And then our other two currents are both flowing out. So we're just going to add those guys together. So that's going to look like 4 amps plus I8. So we have one equation and two unknowns, but we can put everything in terms of that voltage Vx because we just learned that when things are in parallel, they all have the same voltage drop across them, right? And it should be pretty darn easy for us to see here that everything is in parallel because we have what's called a single node pair circuit. That terminology is used a lot in your web work assignments. Anywhere you see for the single node pair circuit above, below, whatever, just realize that means everything is in parallel. That's literally all it means. Okay? So using Ohm's law, how would we express the current I10 in terms of our voltage Vx? So what's Ohm's law? Let's start there. V is equal to I times R. So we're looking for I, so we're going to rearrange slightly. So I think I is equal to V over R is what we're going to use here, okay? So we would have Vx over 10 ohms should our Ohm's law representation here have a positive sign or a negative sign. Positive, because the current I10 is flowing into the positive polarity terminal. Right. Now when we're looking at I8, what should I8 be in terms of Vx? Negative Vx over 8 ohms, because the current is flowing into the negative polarity terminal. We could then substitute those relationships into our KCL equation. So we would have Vx over 10 ohms is equal to 4 amps minus Vx over 8 ohms. So that would be Vx over 10 ohms plus Vx over 8 ohms is 4 amps. I'm going to come over this away. That looks like Vx times a factor of 1 over 10 ohms plus 1 over 8 ohms is equal to 4 amps, or Vx is equal to 4 amps divided by 1 over 10 ohms plus 1 over 8 ohms. So that's what I'm going to put in my calculator. So 4 over 1/10 plus 1/8. And I get 160 over 9 volts. All right, so how do you guys feel about Kirchhoff's current law? Fairly okay. So let's look at one other thing really quickly involving KCL. Let's say that I have a 3 amp current source like so, and then a 5 ohm resistor, and then an 8 ohm resistor. And I'm going to define the current flowing through my 5 ohm resistor as this current I5, and I'm going to define the current flowing through my 8 ohm resistor as this current I8. So if we were to apply Kirchhoff's current law at this top left node, we would see that I5 is simply 3 amps, right? Current flowing into that node is 3 amps, current flowing out of that node, they have to be equal to each other. So I5 is 3 amps. If we apply it over here, we would find that I5 is equal to -8, which means I8 must be -3 amps, and we get the same result if we applied KCL down here at this node. What I'm trying to get at with this simplistic example is that when things are connected in series, they carry the exact same amount of current in magnitude. We really only just need to pay attention to any directions that are defined, right? So now we know why when we have multiple elements connected in series, we treat them like they're in series. They're all carrying the exact same current. So that's our modified definition for a series connection. Okay, so the last thing I want to do, and I understand that I've talked for the better part of an hour and a half straight, is I'm going to work one quick problem that ties all of these three things together. This is literally from a test that was given last year. Okay. So let's say that you have the following circuit. Actually, let's make this thing up here a voltage source. What I want us to figure out is what the quantity IS is equal to. So this is kind of flipping the script, making us think about things a little bit backwards, in as much as instead of trying to find either the voltage drop across a resistor or the current flowing through a resistor, we're now trying to figure out what our source is doing. Okay? So let's think about things as a logical process here. Okay? So my ultimate goal is to figure out what the current IS is. So when I'm trying to find a current, I tend to think about Kirchhoff's current law because it's used to find currents. Okay? So Kirchhoff's current law tells me that this current IS is either the current flowing through the 5 ohm resistor plus the current flowing through the 6 ohm resistor. That's one way to find it. Or it could be the current flowing down through the 8 ohm resistor plus the current flowing down through the 3 ohm resistor. So it's either those two blue currents added together or those two orange currents added together. Is everybody okay with that? Okay. So which of those sets of currents do you think is going to be easier to solve for? Are you saying, so the blue or orange? I disagree. Okay, so let me tell you why I disagree. Okay, we know Ohm's law, right? I feel like we learned it today. You're given the voltage drop across the 3 ohm resistor, and you're given the resistance of the 3 ohm resistor. So I feel like very easily we can get one of those orange currents. Okay, so that current flowing in down here, unless I'm doing my math incorrectly, and I'm not because I can do a fraction with the best of them, is 10/3 of an amp. So now we only need to figure out what the current flowing through the 8 ohm resistor is. That's the only piece of information that we're missing. Is that okay? So we have an 8 ohm resistor. We are trying to find the current flowing through said 8 ohm resistor. So what piece of information are we missing to determine that current? The voltage, okay? So how might we find the voltage drop across the 8 ohm resistor? And let's just arbitrarily define that voltage as positive polarity on top, like so. So when I'm trying to find voltage, I'm probably thinking about Kirchhoff's voltage law based on the amount of information that we currently know in circuit analysis. So is there a way that I can apply Kirchhoff's voltage law to this system to find V8 based on the information that I already have?
Do the law around.
Around the outside, absolutely. So if I write a Kirchhoff's voltage law equation around the outside, I will have negative V8 minus 10 volts plus V3, which is shit. We're gonna make that 12 volts up here. I did it again, and I accidentally gave myself a 0 voltage. I gotta pay more attention. Sorry about that. Let's call that 12. I mean, realistically, it would have been okay, but I want the answer to not be 0 here. Let's see, plus 10 volts is equal to 0, which means V8 is equal to 2 volts. No, it means V8 is equal to negative 2 volts. Sorry about that. Are we okay with that? Okay. So now let's use Ohm's law and tell me what the current flowing down through the 8 ohm resistor is. Will it be 1/4 or negative 1/4? So it's going to be the voltage V8, which is negative 2 volts, divided by 8 ohms. So we will get negative 1/4 because the current is flowing into the positive polarity terminal, but the voltage is negative, which is why we get a negative number. So negative 2/8 or negative 1/4 of an amp. We add those guys together. 10/3 minus 1/4 gives me IS is equal to, change color, computer. All right, it's going to be an orange. It's not going to let me write. Well, whatever. It's 37/12. I don't know why my stylus has just given up on writing for me. All right, my computer's just being weird. Good thing I was done. Okay, so we've talked about all of our circuital laws that we're going to use very extensively throughout this class. You guys have 17-ish minutes or so in order to work on the in-class assignment. Yes, sir.
So coming from the current source, going down, that's why it's negative V8 and wrapping back up to negative. When you're set it up, maybe you get levels plus impulse.
Yeah, so I'm starting at the bottom left-hand corner of the 8-ohm resistor, and I'm just following the outside path. So negative V8 minus 12 plus 10 when I go around the outside in a clockwise direction.